So today we will be starting another chapter, atoms. Okay, so the structure of atom, we say plum pudding model, Rutherford model, Bohr model, in the Maridan, correct? Okay, why we say model? Because it is not possible to see directly and visualize this is how it is going to be, correct or what? We used to think that earth is flat, then we thought that earth is spherical. Still some of us are thinking earth is spherical, not 100% spherical. Still there is some variations. When someone comes and say no, earth is not this way, earth is in another form, and if he gives substantial evidences, definitely we will have to believe that. Honestly speaking, we are all blind believers some way or other way. People used to claim, no, I am a man of science, you guy, you are a blind believer. They used to say, now all of us are blind believers because we don't have any other go. So when someone proposes a better model with this good evidences, definitely we will have to take it for some time. Okay, when someone else comes and changes it, then we will have to believe that. Okay, so previously it was thought that atom, that is the easiest model, right? Plum pudding model. And what is plum pudding model means? That in that area, for that scientist in his locality, plum pudding is the dessert available, ice cream madri. If someone, suppose if that scientist was born in India, then he would have given payasam model, correct or what? Nothing, whatever is there in the atom, everything is jalka bulka, glue, 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 glue. That's it. Okay, so that was the thought in the beginning. Then Rutherford, he is the student of J.J. Thomson. Okay, that guy also will become a periover in future, correct? No? Okay, so really guide is very important. No? If guide is very good, so obviously our potential will improve. That is true. So J.J. Thomson, he found electron, he discovered electron. He said something like this: electron, negatively charged particle is there which is moving around. Okay, all these things J.J. Thomson gave. Now his student Rutherford, he was trying to find what is the structure of atom. So this is a teamwork. Suppose some of us are there. Suppose if you are the project lead, I am also working under you, so you will be assigning some tasks to me, other children, other students also, and the main person, he will be leading the project. That is how everything is. Once if it is done with the evidences, they will write this, document this, and they will present this in front of other reviewers, other people who are just like Einstein. If he is in old age, definitely he will be one of the person who will be reviewing this work, no? Whether that is right or wrong, he will have the authority. Likewise for every consortium, just like a committee, this will be presented in front of them and they will accept, they will ask questions. Likewise, based on that, this will be accepted worldwide. Okay, so Rutherford did some experiment and he failed. Okay, he couldn't find. Then he did it in 1906. Okay, 1906, Rutherford did an experiment. So this lot of discussions will be there in this chapter. Then only you will understand. Okay, just believe, trust me, and just follow the lecture, so that finally you will understand that why I have to study like this. So that Kadamadri, if you study, you will not sleep, you will understand the background behind the chapter. Finally you will feel like, oh, this is very easy. Already this is very easy, but it will not take much time to remember the things if you study like this. Okay, that is the reason. So he tried this in 1906, okay, to understand the structure of atom, and that experiment is called alpha ray scattering experiment. And this was not successful. Okay, this was not successful. So what he did is, he gave this task to his students, Geiger and Marsden. Okay, 1911 he gave this work to them and instructed them to do this experiment, and they did this experiment and they got fruitful results. Okay, so what is that alpha ray scattering experiment? First we need alpha ray, right? Alpha ray scattering experiment. First thing we need alpha ray. So bismuth is a source of alpha ray. If we keep bismuth here, this will start giving alpha ray. Why is it so? Why is it so? Radioactivity. Bismuth is there in the periodic table. Bismuth is there in the periodic table. So all the elements are there in the periodic table. All the elements in the world is there in the periodic table. No. And then why bismuth is there? All radioactive elements are there in periodic table. Radioactive elements are not there in periodic table, right? If this it is there. Example? Okay, see, the thing is, each element will have isotopes. Some isotope will be stable, they will not be radioactive. Some isotopes will not be radioactive, some isotopes will be radioactive. Okay, somewhere around 1500 elements, in that only 250, some around 250 is not radioactive, remaining all are radioactive to attain stability. Okay, so one isotope of bismuth will be radioactive and it will be emitting alpha radiations. So regarding why alpha radiations and all, based on the neutron to proton ratio inside the thing, that we will study in nuclei. That we will in detail study in nuclei. Here I am using bismuth as a source of alpha particle. So this is going to emit alpha particles. Okay, so alpha particles can emit and go in any direction. Correct or what? It can go in any direction. So we need alpha particles. So here what we are going to do is, we will be keeping a gold foil here. We will be keeping a gold foil here. Okay, gold foil is kept to understand the structure of atom. We are interested in the structure of atom in the gold foil. So if it is possible, we are interested to keep one atom. If it was possible, we would have kept one atom, so that we will be able to find the structure of that one atom. But it's not possible. So what we will be doing? We will be trying to reduce as much as possible. So we will be getting a better clarity if it is very lean. If it is very lean, if the gold foil is like this, then it will be able to study. If the gold foil is like me, then what will happen? All the alpha rays will come, hit, go everywhere. Okay, if it is a single layer of gold foil, then it is easy to study. So எடுத்துட்டு அடிச்சு beat பண்ணி எல்லாம் பண்ணும்போது, certain people, after so much of effort also, it is very difficult to get a single small sheet. if you think in that way, gold is better. Malleable nu sollula. You have heard about malleability. Okay, one second. Should we, in order to avoid noise, if we want, we can switch off this fan and put AC, and we can close the door also. Later recording will be affected. So malleable, okay, malleability, that is important. So gold is malleable, so we have chosen gold foil. Okay, so this is bismuth. I am saying this is source of alpha particle, and I am using gold foil. The reason is it is malleable. This is malleable. Now alpha ray should come, but alpha ray will go in different directions, no? So what we do is we will keep lead bricks. Okay, lead bricks. What this lead bricks will do? Lead bricks will attract the alpha particles if it comes near to them. Lead bricks will attract alpha particles if it comes near to them. Clear or what? Okay, clear. So this is called lead bricks. These are lead bricks. Lead bricks, what is the speciality? It will attract alpha particles coming to them. Okay, and this is generally called as collimators. The intention of keeping this is we need straight line alpha particles as much as possible. We need straight line alpha particles as much as possible. Why? Because we are studying about a small particle. Atom is very small, so this is going to be very thin, alpha very thin. Okay, just it will just pass through. Okay, right. Now this is actually zinc sulfide screen. This is actually zinc sulfide screen. This is actually three-dimensional. Okay, just like this. Okay, if I am moving my hands on this is how it is going to be. Okay, it is not like this or like this, it is full. Able to see, able to visualize? Okay, that is how. Why is it so? Because these alpha particles, if they pass through this, say for example one alpha particle went through this and it came here, then this is photosensitive. So if alpha particle hits zinc sulfide screen, what will happen? Flash. But that flash is too small for us to visualize, so what we do, we will have a microscope also. This is going to scan this. So this is what is the alpha ray scattering setup. Okay, clear? So the thing is, suppose this alpha particles comes here, most of the alpha particles will go straight. Most of the alpha particles will go straight. Means most of the space in an atom is vacant. You need not write any notes, just running notes slightly you can note down, but I will give you sentences because those sentences and observations are important, so I will be writing it. Now just running sentence, small short notes you can take, no worries. So collimator, alpha particles. So most of the alpha particles will go straight. So they understood that most of the space in atom is vacant. Some alpha particles will scatter at some angle. Okay, scatter at some angle. Some alpha particles will scatter back, some very less number of alpha particle will reflect back. So based on all these observations, they got some inference and they found nuclei or nucleus inside the atom. There is something called nucleus inside the atom. This was found by this team, or we can say Rutherford, okay, or Rutherford, Marsden and Geiger. Clear or what? And this gold foil will be 10 raised to minus 6 to 10 raised to minus 8 meter thickness. Okay, right. Source of alpha particle, and we need to send this with the good kinetic energy, then only this will come near to this. If the kinetic energy is weak, what will happen? If I need to go to that camera, I will be going like this, and then after that what will happen? I won't be able to move further, correct or what? But if I am going with the energy, I will be able to move near to it. So how much is the kinetic energy of this alpha particle? That much closer this will go. What is distance of closest approach is there? That also we will find. Distance of closest approach means how much near this is going to go near the nucleus. So kinetic energy of alpha particle will be between 5 mega electron volt to somewhere around 7 mega electron volt. Okay, this portion definitely you should read from NCERT once, not once. How much time you need? That much time. Okay, clear or what? Because these all values please take from NCERT, from whatever information you get, always stick to the information given in NCERT. Okay, clear? So 5 mega electron volt to 7.7 mega electron volt will be the kinetic energy of the particle. Okay, so scattering will occur. Okay, so if you need, take down this figure if you do not know, but if you have, don't waste time. Okay, and suppose if this is scattering angle, say for example theta 1, if this can be another scattering angle, this can be another scattering angle, likewise. Okay, fan of it is no. ഓക്കെ, എനിക്ക് ഓഫ് ചെയ്യണ്ട, ഓഫ് ചെയ്യണമെന്നില്ല, ചുമ്മാ AC കണ്ടിന്യൂ ചെയ്യോ, പക്ഷേ AC ഓഫാക്കിയിട്ട് AC ഓണാക്കിയിട്ട് ഫാൻ ഓഫ് ചെയ്യും. ക്ലിയർ? Okay, now let us interact. Okay, you sit there. இது question கேட்குறது ஆன்சர் சொல்கிறது அந்த மாதிரி கிடையாது. இது நமக்குள்ள we discuss politics also, no? Correct, no? Politics regarding masters. விஜய் ஹீரோ நடிச்சுட்டு, ஓகே, ஆனால் ரோல் வந்து விஜய் சேதுபதி இஸ் டூயிங் எ வில்லன் ரோல் அண்ட் ஹீ இஸ் கேப்சரிங், அந்த மாதிரிலாம் டிஸ்கஷன் பண்ணுவாங்கல்ல. ஸோ எப்படி யார் உங்களுக்கு பிடிக்கும்? விஜய் பிடிக்குமா, விஜய் சேதுபதியை பிடிக்கும்னு சொன்னீங்கன்னா, ஸோ சார் நோ டோன்ட் ஆஸ்க் கொஸ்டின்ஸ் நீங்கள் சொல்லுவீங்களா? சொல்ல மாட்டேன்ல, ரொம்ப சந்தோஷத்தோட சொன்னல. So for till NEET, this is Vijay and this is Vijay Sethupathi. Okay, so remember like that. So I will ask the questions. Okay, Papa, your good name? Okkara venda, alla sorry, nikka venda. Okay, sit. Akshara. Akshaya. Okay. Akshaya, bismuth. Why we are using bismuth? What is the use of bismuth? Source of alpha particle. Okay. Pakam, neighbor? Gayatri. Sit. Mukandate solunga. How much should be the approximate kinetic energy of this alpha particle? 5 to 5 joule to 7.5 joule. Correct thane? Correct? 5 mega electron volt to 7.7. 5 mega electron volt to 7.7 mega electron volt. Discussion. You need not study also. Fine. Your name I forgot. Aishwarya. Your name? Vishaka. Vishaka. Vishaka, what is the use of this lead bricks?
It is used to send the narrow alpha particle to the gold foil.
Adukku enna sonna technically what do we say? Collimation. Okay. Collimation nu sollu. Okay, so that is the collimation. Okay. Right. Why we use gold foil here? Tangam? Why we use gold foil?
Highly malleable.
Malleable, very much malleable. Okay, that is the answer for that. Right. Approximate thickness of this gold foil is 10 raised to minus 6 to 10 raised to minus 8. So have you all noted down these points? Okay, this is the thing which we need from this. Right, shall we move to further discussion? Okay, right? Okay. So zinc sulfide, why we are using zinc sulfide? That is photosensitive, correct or what? Can you tell me any other photosensitive material? Barium sulfide. Okay, this also can be used. So add there barium sulfide. Okay, and platinum sulfide also. Platinum sulfide also. Platinum sulfide. Okay, barium sulfide and platinum sulfide. Okay, any photosensitive material which is suitable. So these are the things given. Okay. Okay. What is this alpha scattering angle? Alpha is scattering angle. Now we'll get into the business. Okay. Okay, so next thing is scattering angle. Scattering angle. So this scattering angle, they have got some experimental values. Okay, so first experimental value, say suppose if it is 0, somewhere here 10 raised to 1, then 10 raised to 4. Likewise, suppose you have written 10 raised to 7. Okay, 10 raised to 7. So this value they got, and this is the angle, scattering angle. This is the number of alpha particles. So for each scattering angle, they got different number of alpha particles. Say for example 30 degree, some number of alpha particles, 60 degree, some number of alpha particles. Likewise, some values are observed. Okay, so one is at 0 degree 10 raised to, say, okay, suppose if this is 20, 40. Likewise, okay, I am writing up to 180. So somewhere around 100, suppose if we get like this, okay, somewhere around 100 if we get like this, these two are experimental values. These two are experimental values. Okay, only not those two, some are actually, some values are experimental values. So maybe beginning and at the end we can say they are all experimental values they observed. In between also certain things they got, remaining all the things they did through theoretical calculation. So this is not straight line, this is not straight line, okay, not straight line. So from this they got the number of alpha particles scattered at some particular angle. Okay, so that we will write is equal to a z square divided by sine raised to 4 theta by 2. Okay, this is the number of alpha particles scattered at this angle. So here n is the number of alpha particles. N is the number of alpha particles, and scattering angle, okay, is the atomic number. What is atomic number? What is atomic number? Number of electrons or protons? Atomic number, that is one thing. Yaroda atomic number, this one. Alpha particle or bismuth. Gold foil. Gold foil. Okay, based on the gold foil.
Yeah, gold foil.
Because we are studying about the structure of gold foil atom. Later we understood that even if we keep some other malleable metal also, we will be getting the same thing. So whichever thing we are keeping, that foils atomic number. Okay. Specifically, when we ask what is atomic number, you may say number of protons or number of electrons. That is true for a neutral atom. That is true for a neutral atom. Precisely speaking, everywhere 100% valid statement is number of protons. An element will be element based on the number of protons, not due to electrons. Electrons, if it is removed, that will become plus. If it is added, that will become negative. Okay, so there if we take the number of electrons, it will go wrong. Okay, so atomic number means whether it is He plus or lithium plus plus, we don't need to worry. It is going to be the atomic number of helium or atomic number of lithium. Okay, if we study that number of protons is the number of atomic number, means when we see lithium plus plus, what will happen? Lithium plus, whether there is any change in the atomic number, we will get unnecessary confusion. So be very solid in the basics. Number of protons, okay? Atomic number means number of protons. So here atomic number of the foil, okay? Atomic number of the foil, okay? And this so need not worry about constant, that you will understand while we do questions. Okay, we don't have much discussion about that constant. Okay, leave it. Clear? Okay, fine. Now start, right? Observations. So this formula is important, children. 4 questions will come. This formula is important. N is equal to kz square sine raised to 4 theta by 2. Okay, it's important. Clear? Now observations. Number 1 observation. Number 1. Most of the alpha particle. That is somewhere around 6%. Okay, went undeviated. Okay, so this is observation number 1. Okay, so right, observation number 1, most of the alpha particles, that is around 99.86% went undeviated. Now what we will do, under this observation we will write the inference. Okay, inference. Most of the space in atom is free. Okay, most of the space in atom is free. Most of the space in atom is free. So thing is like see, suppose if it is a big space, okay, alpha particles are coming, only I am standing there. Okay, very big space, all of them are passing down, then we will understand that only this space is occupied by someone. So around 99.86% of atoms, alpha particles went without any deviation. Means just imagine, most of the space. Okay, proportionately if we take, almost 99.86% of the space will be what? Free. Not exactly, but still we can say. Okay, so that is the inference they get. Okay, taking inference also needs thoughts, right? Okay, that is why. So this is observation 1, based on the inference. Second one, observation 2. Observation 2. .14% of alpha particle, 0.1, okay, observation 2, 0.14% of alpha particles, 0.14% of alpha particles deviate okay, more than okay, so theta is greater than 1 degree, more, almost, that is 0.14% of alpha particles deviate more than 1 degree. Now before writing the inference, we will write inference of observation 3 is 1 in 8,000 alpha particles. 1 in 8,000 alpha particles deviate more than 90 degree. Okay, 1 in 8,000 alpha particles deviate more than 90 degree. Now observation 3, 1 in 10 raised to 6. Observation 4, 1 in 10 raised to 6 alpha particles deviate about 180 degree. Okay, about 180 degree. Okay, clear? Now for all these things putting together, Okay, some deviation is there. Okay, some deviate very less. At least 1 in 10 raised to 6 alpha particle is deviate about 180 degree, means they come back. So here very strong inference is very powerful, is nothing but positive charge is concentrated at the center. Okay, so the inference is positive charges are concentrated at the center. Positive charges are concentrated at the center. Positive charges are concentrated at the center. Correct or what? Okay, so right. Okay, now certain things which you can understand. Positively charged particles are concentrated at the center means it is not just a normal concentration. It is very dense concentration. Why? Because see, alpha particle is moving with so much of kinetic energy. So alpha particle means what actually? Alpha particle is what? Helium nucleus. Helium nucleus, right? Helium nucleus alone means without electrons. That is, they are positively charged particle. Positively charged particle. So alpha particle is positive. So when an alpha particle, if it is going like this, and here if something is there, after reaching some distance, if it is to be come back, then there should be alpha particle is going like this, deviating like this, going like this, deviating like this. Most of them are passing like this. 1 in 10 raised to 6 alpha particle is going like this, then returning back. So returning back requires very strong electrostatic repulsion. Very strong electrostatic repulsion. Otherwise this is not at all possible. Okay, very strong electrostatic repulsion. So F is equal to what? K Q1 Q2 divided by what? R square, no? Electrostatic repulsion. So both are like charges. That is the reason it comes here, then it returns back. So we understood that very strongly concentrated, positively charged center is there in the atom. Okay, so that is the inference of this. Okay, so note down, strong electrostatic repulsion must be there in order to get a deviation of 180 degree. Okay. Okay, clear? So they understood that this is not electron. What our sir, they call names only, they don't call sir and all, right? Outside universities, if you go and study, we can call by name. Okay, called by name, we can, it is just that kind of relation. Okay, so we will be calling by name, no? So in our language we can say our sir said electron that is negatively charged, this is something else, so we will put a new name. So they put a new name, nucleus, and they said that is at the center of the atom. Clear? So that is how Rutherford found nucleus. Rutherford found nucleus. Okay, okay, positively charged, very densely concentrated center which is called nucleus. Clear? Done. So this subsided plum pudding model. This one subsided plum pudding model. So plum pudding model became invalid after the proof of this one. Okay, so now you can take this simple question. Okay, 1000 alpha particles. 1000 alpha particles. Okay, 1000 alpha particles are scattered at 60 degree. Okay, scattered at 60 degree. Okay, find the number of alpha particles. Number of alpha particles scattered at 90 degree. Okay, if 1000 alpha particles are scattered, okay, at 60 degree, find the number of alpha particles that is scattered at 90 degree for the same foil. Okay, for the same foil. For the same foil. Mukesh, just can you close that? Okay, so 1000 alpha particles scattered at 60 degree, then find the number of alpha particles scattered at 90 degree for the same foil. So okay, so take in the options. So here n is equal to k z square by sine raised to 4 theta by 2. So this is constant, this is also constant, no, because same foil we are using. So n1 by n2 is equal to sine raised to 4 theta 1 by 2 divided by theta 2 by 2. Here this is sine raised to 4 theta 1 by 2. Correct. So n is going to be 1000 and this is going to be n2, and how much is this angle? 90 degree. So sine 45. Sine 45 raised to 4. So 1 by root 2 all raised to 4. This is going to be 60 degree. So sine 30. 1 by 2 raised to 4. So simplify this. How much you'll be getting? How much pa? 2 How much? Okay, n2 is going to be, okay, this will come here and this is going to be 1 by root 2 raised to 4 into, okay, 1000. Correct or what? So this is 1 by 4, 1 by 16 or what? This is how much? 1 by 16, right? 16 into, if we square raised to 4 of this is what? Square is 1 by 2. Otherwise this is going to be 1 by 4. So the 4 will go here and this is going to be 1000. 4 cancel. This is nothing but 250. Correct? 1 by root 2. Okay, sine 90 by 2. Sine 45 raised to 4. Clear? Okay, clear? Now we will write the results of Rutherford's model. Till a part it was so good in explaining the nucleus, it is successful in that terms, but after that certain points were having mistakes. So that was dealt by Neet board. He came and he corrected them and he got Nobel Prize also. So that discussion we will do. From that discussion we will get into Bohr model of atom. Okay, so point number one, you need not write all that, just to give just hints. Okay, point number one is what? Most of the space in atom is empty. That is number one. Okay, most of the space in the atom is empty. The reason for that is most of the alpha particles went undeviated. That was the first result. Okay, second result is around 0.14% of atoms deviated more than 1 degree. 1 in 8,000 atoms went deviated more than 90 degree, and 1 in 10 raised to 6 at alpha particles deviated 180 degree. Okay, so from this the second strong result came. Positively charged nucleus, or to positively charged, okay, center, okay, called nucleus. Okay, positive charged particle is concentrated at the center, that is nucleus. Okay, that was the second result. Clear? Third result is the number of alpha particles deviating, that formula. Okay, so one thing is this size of the nucleus. Second result is what? The size of the nucleus is very small, because only one particle in 10 raised to 6 deviated back, remaining all the things at least deviated. So the size of the nucleus is very small. Okay, most of the atom is free. First result. Second result is the size of the nucleus is very small. Third result is the positively charged particle is concentrated at the center. Okay, third result. Fourth result is the number of alpha particles scattered at for a particular angle is what? N is equal to kz square by sine raised to 4 theta by 2. That is the third observation, right? Fourth observation done. Now from fifth observation, so till now whatever we have discussed you are clear. Any doubts so far? Is it clear for all of you? Okay, from next onwards, okay, the thing starts. Okay, he said fifth one. Okay, the electrons are attracted by, okay, the electrons are attracted by the positive nucleus, but electrons don't move towards, nucleus. Okay, but electrons don't move towards nucleus. Okay, so he said electron utilizes this force. Okay, see, electron is moving, some attraction is there towards the nucleus, but still it is not falling towards the nucleus. So what will happen? It will lead to what? Circular motion. It will lead to circular motion. Suppose, see, just for your understanding, suppose if some, here just imagine this is earth, okay, some celestial bodies, suppose if it is coming like this, now it wants to go straight, so here even it attracts, what will happen? It will not fall down towards it, will never fall down towards it. Its tendency will be to go straight. So it wants to go straight, but attraction is there, so what will happen? It will bend. So at every position this phenomenon happens. It wants to go straight, but it attracts, again it bends. Wants to go straight, but it attracts, it bends. Finally what happens? It will stuck up in circular motion. This is the fundamental for any circular motion. If something is moving, if from at a 90 degree angle, if there is some attraction, what will happen? It will get into stuck up into circular motion. Examples, gravitation. Number 2, your force in electromagnetism, moving charges and magnetism. Moving charge entering the magnetic field is getting into circular motion. So everywhere this happens. Okay, so electron is already moving, nucleus is attracting, but it will not fall into the nucleus. What will happen? This force, electrons are attracted by the nucleus. Okay, yes, this force is utilized what? Centripetal force. This force is utilized as centripetal force. Centripetal force. Clear or what? This force will be utilized as centripetal force. So Fc is equal to Fe. Fc is equal to Fe. This is one result. So he said that. Okay, so very major contribution. Okay, clear? Sixth point is distance of closest approach. Distance of closest approach. Say for example, if atom is here, if this is an atom, from very far distance this alpha particle is coming. So what is the potential energy of this alpha particle? Consider this as large distance. From this alpha particle is coming. Understood or what? Alpha particles went near to it, not able to go further. Then it will have to go back 180 degree. So with such energy alpha particle went, then after here it returns back. So this distance is what? Distance of closest approach or not. That distance is what? Distance of closest approach or not. Now tell me, what is the potential energy of this alpha particle here? Clear ah solunga? Say clearly, very boldly. Yes sir. Appadi sollula army people. Same way. Even after becoming doctors, you can become collectors. The recent trends is that those who become doctors, again they will prepare for civil service and they become collectors also. There are a lot of collector doctors. So you can keep high, very heavy dreams and all. Okay. So appadi yosikkumbodhu you can be very bold. Okay. So solunga. Appadi solittu irundha collector aga mudiyadhu. Okay. Tell me, what is the potential energy of this alpha particle? Electrostatic potential energy. How much it will be? KQ by R. KQ by R. KQ by R. So this is very far, no? Large distance solumbodhu adul oru hint irukku. What is that? So while even if you get problems like this also, you can apply the same thing. Large distance means JP sir, no? JP sir. JP sir might have taught potential energy, electrostatic potential is what? The work done to bring a charge from infinity to the point. So he might have said, when you are seeing the potential at a point, the potential at infinity, potential at this point. So potential difference or potential energy or potential at that point is nothing but the potential at this point minus potential at that point, and at infinity what is the potential? Zero. Okay, so that is potential. Now regarding potential energy also, this is work done per mass. work done per charge. Gravitational potential is per mass, electric potential is per charge. Everything is easy, all are connected. So here this one is the work done to bring the charge from infinity to this per charge illa. That is the only difference between potential energy and electrostatic potential. Electrostatic potential is also difference. Electrostatic potential is also potential difference. Electrostatic potential energy is also potential difference. Okay, so very clearly I could write that here the potential energy is what? 0. Correct? No, 0. What about kinetic energy here? Oh, we know, right? We know actually 5.52 or 7.7 mega electron volt. So kinetic energy will be there. Okay, just put a tick. This is nothing but kinetic energy. Okay. At this point, what will be the kinetic energy? What is it? What I am doing? Disco. What I am doing here? Alpha particle is trying to move, not able to move. What is the kinetic energy? 0. So kinetic energy final is 0. Kinetic energy initial is something is there. What about the potential energy here? This thing you can say. A, Q1, Q2 are not square potnuma. Okay, field, force, potential energy. Ellam jalka bulka avakudadu. Okay, K, Q1, Q2 by R0. Okay. So suppose what is the charge of this? Can I say this is going to be ZE? Okay, this is going to be ZE. Leave it. Okay, we will deal that. So this is final potential energy, this is initial potential energy, this is initial kinetic energy. Okay, note down this. Okay. So here, what is Q1? Charge of alpha particle, right? Charge of alpha particle. Okay. Alpha particle is what? Helium nucleus. How many electrons were there in helium? 2. So helium nucleus means 2 electron gone. So how much charge will be there in the helium nucleus? Plus 2e. So this is nothing but 2e. Correct or what? Here what atom? What kind of atom is this? Either gold or any malleable material. Let them decide that. So the atomic number into E, that is a charge. So Q2 is the charge of foil atom. So whatever be the atomic number, this one to E. Correct or what? Because we are dealing with the nucleus alone. Atom is neutral. But this is nothing but what? Charge of neutral atom means it is nothing but nucleus. Okay. So is the accurate writing. Charge of foil nucleus. Right. Now things are done. So initial kinetic energy plus initial potential energy is equal to final kinetic energy plus final potential energy. This is 0. So this is K. This is also 0. K is equal to K into, what shall we write? 1 by 4 pi epsilon naught. If you want that can be done. or otherwise you can remember also. Okay, so if we write K is equal to what? Potential energy. So K into 2E into ZD by R naught. So from this what we will be getting? R naught is equal to what? K into 2 into ZD square divided by kinetic energy. So we can write that R naught is equal to 1 to 2 Z E square divided by 4 pi epsilon naught into kinetic energy. This is the distance of closest approach. So if you don't do jalka bulka with the kinetic energy and electrostatic constant, you can remember the like this also. So enna agudadu exam hariyile kinetic energy should not come here, and you should not feel like, oh, this is so easy, sir has given some wrong formula, maybe mistake, cancel easy. Okay, right? It should not do that. So that is the reason this is safe. Distance of closest approach. Right? Clear? Shall I erase this? No? Done? This part? Okay, right. So see, we can say that when kinetic energy is maximum, okay, distance of closest approach will be minimum. Correct or what? When kinetic energy is more, if the alpha particle is coming, if it is very strong, it came near to this. Alpha particle is very simple. Came here, went back. Okay, so how much is the energy? That much near it will go. Okay, when kinetic energy increases, distance of closest approach will come down. Okay, imb. Right, imb. Clear or what? Okay, so they got the information after doing this experiment that they found that distance of closest approach is somewhere around 30 into 10 raised to minus 15. That is somewhere around like a 30 Fermi. Okay, somewhere around like a 30 Fermi. That is the distance of closest approach they got. Okay, minimum. Okay, so they understood that if this is the distance of closest approach is 30 Fermi, definitely nucleus, the size of the nucleus will be less than this. The distance of closest, this is came back, right? Okay, without doing any damage, it came back, means understood that this has gone to the nearest distance. So that gap is what? 30 Fermi means definitely the size of the nucleus we are taking this as spherical. Size of the nucleus we are taking as spherical. So we understood that, okay, if this is the distance of closest approach, definitely the size of the nucleus will be lesser than this, and later found that this much only Rutherford can say. When this has happened? 911. So long, right? So many years back. So sophisticated, nothing. This was the thing for me, and later 6 Fermi is the size of the gold nucleus. Later it is found that 6 Fermi is the size of the gold nucleus. So okay, actual size of the gold nucleus is found as 6 Fermi. So their estimation is really good, right? That is what. Okay, right. Okay, clear? Okay, now how many numbers results? How many numbers it is now? 6. So from 7th onwards, actually they were certain things were not right. So you can put drawbacks. It is not just for even for board exams also we will be writing drawbacks, right? This is not like that. These are concepts. So with these drawbacks we will have to move into Bohr model. So you put the heading drawbacks and write as the 7th result or 7th point. That is not actually result because they are wrong. Okay. Okay, so 7th one. Okay, so that is actually the first drawback. Okay, first drawback. He couldn't explain the stability of atom. Okay, we can say drawback. Okay, number 1 drawback. He couldn't explain stability of couldn't explain stability of atom. So the thing is, we should understand that electromagnetic waves, electromagnetic waves comes before this. So from that we should understand one point. If you do not know, learn it now. Maxwell, okay, he proved that an accelerated charged particle will emit radiation. Accelerated charged particle will emit radiation. It is just like the process is coming like that. A charged particle at rest, okay, will experience electric force. If field is there, it will experience an electric force. Okay, done. A particle at rest, will it experience magnetic force? No. But charged particle starts moving, it will experience magnetic force and it will move. Correct or what? Because QVB, Q into V cross B. But if it moves with an acceleration, that is the third case. Charge at rest, electrostatics. Charge is moving, moving charges and magnetism. If it starts moving with the acceleration, electromagnetic waves. So there it will emit what? Radiations. Maxwell has pointed this. Okay. Maxwell has pointed this. An accelerated charged particle will emit what? Radiation. Correct. Now here actually this electrons, this nucleus is there, electron is there, this is with acceleration, this is moving with the acceleration. So what should happen? If it is emitting radiation, finally it will not be able to continue like that. What will happen? See, this is what it is going to happen. It will happen, it will emit and it will keep on emitting radiation. Finally it will jump into the nucleus. Okay, it will jump into the nucleus and suicide. Then it will not be atom. Atom will not be there. So approximately this should happen in 10 raised to minus 8 seconds. Okay, so what happened? Rutherford said, okay, with this explanation, Rutherford was conveying the message that the electron is moving with the acceleration. Okay, that much he said. Okay, but there is no proper explanation for the stability of the atom. Atom will continue as atom. Okay, there should be some reason. But if it is having what? Acceleration, and at the same time if it is emitting radiation, what will happen? It will jump into the nucleus. Okay, so this is one drawback. He couldn't explain that. Clear? Understood? Okay, clear? Next drawback, second one, he couldn't explain discrete spectrum of atom. discrete spectrum of atom. That is nothing but just like our in chemistry, what we do if we need to find about some element. Okay, what we do, salt analysis or chemical reactions we will be doing, we will be taking test tube, we will be doing all that. Okay, yellow color, red color, this is the thing in chemistry, right? But in physics, we analyze them in a different way. Okay, so just like our fingerprint, my fingerprint is different, okay, your fingerprints are different, all are having different fingerprints. So atoms also have such identity card. Okay, nature's identity is there for atom. Okay, each atom will have something different. So what happens is, suppose if we just like doing in a test tube, suppose if you take a atom gas or atomic gas or gas atoms, if you take in something and if you heat it, it will get some energy. So it will start emitting some radiations. If you parallelly keep a prism, what is the thing of prism? It will disperse, no? It has dispersed. So it will disperse, and if we keep a screen, we will get different available colors or wavelengths. Correct or what? So this is the idea. So when we do like that, actually we are getting discrete spectrum. Discrete spectrum means, okay, suppose Prabha is suppose one wavelength, 4000 angstrom. Immediately Bru 5000 angstrom. Okay, then Preeta 6000 angstrom. Okay, then I am seeing in the middle of them, what happened to 4001 angstrom? Where is 4999 angstrom? They are all missing. So atoms doesn't emit those radiations. That is called a discrete. Continuous means Prabha is 4000 angstrom, Brinda is 4001.0001 angstrom. So close. Okay, next Preeta is another shade, 4002 angstrom. It will be continuous. So when we just hit the atom is emitting radiations not as continuous spectrum but discrete spectrum. So he couldn't explain all that. Okay, he said the mistake is, he said Rutherford said electrons circulate in any orbit. He said, Rutherford said electrons, see Rutherford, according to Rutherford, electrons, okay, circulate in any orbit. Electrons circulate in any orbit. Any orbit means, what is the problem? Idella oru problem. These are all problems. If they haven't considered them as a problem, we could have avoided studying this chapter. Okay. He said, electron will circulate in any orbit. Any orbit is solving. Boss said. Correct or what? Don't say any. You should be very specific. Okay, so he said if this is positively charged nucleus, okay, if electron is circulating in any orbit means, everything is possible. Okay, the problem with this is, this orbit is nothing but train track, track. Okay, so that rail track is constructed. So electron is also moving in a similar track, no? If you look at the microscope, can we see some tracks there? Concrete tracks, chinna concrete tracks, specific magical concrete tracks. These are actually what? Energies. If electron is having an energy, say for example, okay, minus 13.6 electron volt, then this will be moving in this line. Track, the orbit of electron is actually an energy. Okay, minus 13.6 electron volt may be one energy. Then after that, electron simply cannot move in the next energy. It needs specific energy level. So say for example minus 3.5 volt. Okay, so this orbit is nothing but one energy. Okay, and if it is changing its track, that is another energy. Electron is very choosy. It will not move in everything. Say for example, if there are some platforms, I will do like this if someone is sleeping. Okay, so avangala paathutu yen thambi thoonga kudadu, please don't do like that, he will get offended, right? Correct or what? Ellathukku munnadi naan thoonguradhu avlo thappa nethu mudichu padichen. Okay, so what I do, I will make some voice, so some sound, so if possible, fortunately, that sleeping baby may understand. Those who are sleeping, please stand up. All of you, please look here. Okay, so this is like suppose a train is romba mask inga poda venda inga just okay ini ingem potittu eduthu thoonguvaanga. Okay, so look at this. Suppose if a train is all the trains moving to Chennai, suppose if you are choosing a platform like number 1, number 5, number 10, number 15, is it a continuous spectrum or discrete spectrum? Understood or what? Okay, so it is not like all the trains will be 0, next 1, 2, trains will not move like that. Okay, the moves to Cochin, trains to Cochin will be moving like first platform, 5th one, 10th one, 15th one. So discrete. So first platform, here it is physical platform, instead of that is put energy. Minus 13.6 electron volt track, no, there only world is advancing. So one day we will say that energy in the first platform is minus 13.6, let that train go in that way. Likewise, clear or what? So he couldn't explain all that because he said any orbit means there are chances that electron can move in this orbit also. Understood or what? Very close. Any orbit means any energy is possible. But when we do kilu, atoms are not emitting any energy. It is emitting only discrete spectrum. Clear? So we will discuss that further. Okay, now this is the thing. Understood or what? He couldn't explain discrete spectrum. Okay, according to him it was continuous spectrum. Okay, clear? Okay, so what happens is, suppose if an electron is here, suppose if this is minus 13.6 electron volt, if we throw some energy, suppose if you are sending photons are what? Energy. They are also radiation, considering the particle nature. Okay, எனக்குள்ள என்ன இருக்குது? ஒரு மனிதனும் இருக்கு, எனக்குள்ள ஒரு மிருகமும் இருக்குன்னு சொல்லுவல. I am an animal sometimes, at the same time I will be a human also. அப்படி சொல்லுவாங்கல. So a particle may have the properties of wave also, at the same time properties of matter also. So energy is actually matter, but energy is actually wave. Both are there. So photon we are sending, photon is coming, okay. So minus 13.6, this photon was giving only 0.2. What electron will say? Are go. Electron is very choosy. Adala saapida maata. But again, if you are throwing photon, just think it as an ice cream. Okay, vanilla. He doesn't like vanilla flavor. He didn't choose. Chocolate flavor. Okay, electron happily received it and jumped to this orbit. Then I said, why is it so? When I gave vanilla, he was not jumping. When I threw him chocolate, he was jumping. I took chocolate ice cream, I just saw how much energy is there. I understood that how much orbits, that much was the energy of the chocolate. That is why electron jumped. Understood? The electron will jump to the next orbit when he gets the exact difference between the energy of two orbits. Clear or what? This is the idea there. So electron is very choosy. Okay, same thing here. Next orbit. How is this path? Those who know, 1.5 electron volt, right? Theriyuma? Okay, 1.5 electron volt. We will discuss that. Okay. So suppose, what is the difference between these two? Say for example, how much? Say for example 2. Okay, 1.5 or 1 point some values I may not remember. Suppose if you are giving again chocolate we gave, now he was not eating because he cannot jump from here to this with the chocolate ice cream this time. So we took butterscotch. I threw butterscotch. Again he did not accept. Then I took that chocolate chips, that I mixed it and I took 2 scoops of that with the chocolate sauce on the top of it. Chocolate. Okay, so I mixed it and I threw. This time he jumped to this. Clear? So how energy of that one? 2 electron volt, right? Then only this will jump. Correct or what? In inga vandadukku appuram anga poi mall ella ukandittu irukku. Okay, Brooksfield Mall, on the top of it got so much energy. Romba neram ukandittu irukumbodhu not getting stability on the top. No, we are feeling padikala, Neet coaching is there, I am wasting time here. Took a phone call, Brinda, what are you doing? I am sitting and studying. Oh apdiya, okay, cut it. Stability illa, nimmadi illa, mana nimmadi illa. What we will do? This electron will jump back, emitting sound. How much energy? Same difference of energy it will emit and it will jump back to this one. Okay, மறுபடி என்ன இல்ல, நீங்க இன்னும் படிக்கணும். எனக்கு நிறைய எல்லாம் ஊர் ஃபுல்லா world should be doing. KGF பாத்திருக்கா? Okay, I should rule the world. I need the whole world. Everything I need. நிம்மதி இல்ல, மறுபடியும் jump back to this. கடைசில என்ன ஆச்சு? நிம்மதி ஆயிடுச்சு, எல்லாமே போச்சு. Okay, with low energy he can move here. So this is the idea of continuous spectrum and discrete spectrum. Okay, so in the way you remember, you can just note those things down. Okay, so moving to the higher level, it needs energy. So it will accept photon, it will move to the another one. When it needs to come to the lower one, it will emit radiations. Okay, emit radiation. Those radiations are called photons. Okay, so photons, the energy of photons are generally say hc by lambda. hc by lambda. Can I say this photon or hc by lambda? It will not accept every photon, right? We don't consider all the photons. We will be considering only those differences. Can I this as En2 minus En1? Correct or what? So energy of photon emitted or absorbed. Emitted or absorbed. Okay, will be this. Energy of photon emitted or absorbed will be of this. Clear? So these were the drawbacks of Rutherford, mainly regarding continuous spectrum and discrete spectrum. But contribution of Rutherford, was it significant or not? So much, right? A person, no one can do all the things in his lifetime. These are all their lifetime project and achievements. Okay, so full life will be given for that, right? So next one is Bohr model. model of atom. Okay, so Bohr came and corrected, and he gave the first statement: electrons will revolve only on stable orbits. Okay, that is the first statement. Okay, electron can revolve only on stable orbits. Electrons can revolve only on stable orbits. So this statement naturally will take many things out, right? Many problems in the Rutherford model this can settle. With the proper basics and fundamentals, I think you might have understood. Okay, stable orbit means naturally discrete spectrum will be explained. Okay, so this is the first statement. Okay, so electrons can have fixed energy levels, and naturally whatever you are studying, K, L, M, N, right? 1, 2, 3, 4. So just like it will be moving. That is the first statement here. Okay, second statement he said is electrons will have same energy as that of the orbits. Electrons will have same energy as that of the orbit. Okay, same energy as that of the orbit. Electrons will have the same energy that of the orbit. Third one, while revolving in a particular energy level, electrons do not emit radiations. While revolving in a particular energy level, electrons do not emit radiations. Okay, so when it is moving around a particular energy level, that is in the same orbit, that time it will not emit any radiations. So Maxwell's statement was okay for classical physics. Okay, but here this is quantum physics. Quantum physics means these events are happening in a small thing which is of the order of Fermi. Okay, so same force of attraction, nuclear force you will study in the atom nuclei. Okay, we have studied about gravitational force, we have studied about the electrostatic force, but nuclear force is there. At a very short distance this will become attraction, but again further short distance and further large distance, large means all in the form of Fermi, 10 raised to minus 15, 10 raised to minus 14, 10 raised to minus 16, 10 raised to minus 13. This is the range of play. Okay, so this is very short range force. So once it will become attractive, further if it is very close or little large, this will become repulsive. So all these phenomenon this happens only where? In quantum physics. So this is modern physics, this is called quantum physics otherwise. So there the nature or the theory of Maxwell that charged particle will emit radiations is not valid for this one. If it is moving in a circular orbit in a particular energy level, this will not emit radiation. This will not emit radiations means atom will be stable, no? It will not come and sutti, it will not do what? Jump into the nucleus, it will not suicide. Correct? So it is bold, it is very strongly moving in a stable orbit. Person is very strong now. Okay, so that is what is the next explanation, third explanation. Clear? Okay, so along with this you should add, if there is a chance to forget that, electrons will be, atom will be stable. Atom will be stable. Electrons will not lose energy and it will not jump into the nucleus. It will not fall into the nucleus because electron is stable. Okay, now fourth one is if electrons absorbs or emits radiation, it will change into the next orbit. Okay, if it absorbs or emit energy, it must move to different energy levels. It must move to different energy level. When electron absorbs, okay, fourth point is if an electron absorbs or emit energy, it must move next energy level. Okay, so these things are clear. Next one is defining stable orbits. Defining stable orbits. Okay, that is, electrons can revolve only in those circular orbits. Electrons can revolve in those circular orbits for which the angular momentum, orbital angular momentum of electron, okay, electrons can revolve only in those circular orbits, okay, where orbital angular momentum of electron is integral multiple of h by 2 pi. Okay, so how they choose the energy, okay, which orbits they will choose, that is done by h by 2 pi. Say for example, this is possible, suppose if the energy, okay, orbital angular momentum, if they are h by 2 pi, this will be one orbit. Another possibility is 2h by 2 pi, orbital angular momentum. What is angular momentum also I will tell you, no need to worry. Okay, orbital angular momentum of shells or an energy level or an orbit should be what? Either h by 2 pi or 2h by 2 pi or 3h by 2 pi and so on. It should be nh by 2 pi. Okay, orbital angular momentum should be 1h by 2 pi or 2h by 2 pi or 3h by 2 pi, so on. It should not be 1 h by 2 pi. 1.5 by h by 2 pi, it will not be stable orbit. Okay, going to a shop, they are saying either buy 1 kg sugar or 2 kg, ka kilo, muka kilo, we won't say, we won't give. Likewise, okay, so angular momentum, orbital angular momentum of electron should be integral multiple of h by 2 pi, then we can say they will be stable orbits. Clear? So this Planck's constant h value, you know, right? 6.626 into 10 raised to minus 34. Okay. Okay. What is the letter we use for angular momentum? L. So simply completed this one. Okay. Shall I erase? So this is nothing but L is equal to, L must be what? NH by 2 pi, NH by 2 pi. Clear? Okay, right? So this is the thing. N is nothing but that orbital number, that should be integer. Okay, integer, this N must be integer, integer, same as what? Orbit number, orbit number, or we can say this is shell number. All are fine. Okay, integer, orbit number or shell number. Clear? Okay. Joshua sir, time आया. Okay, so regarding angular momentum, orbital angular momentum, we will further discuss again after the break. Okay, right, thank you.